Today we're going to be learning about electron configuration, which is the way that we write the location of different electrons in their energy levels around the nucleus of an atom. And every element is going to have a specific electron configuration that shows us how its electrons are organized. So to start off, we need to understand the difference between the different types of sublevels. If you look at the bottom right of the screen, you'll see these different shapes. These shapes are the shapes of orbitals within the different sublevels S, P, D, and F. And S is the most simple sublevel, and it can hold 2 electrons, which is the smallest sublevel that we'll see. And P comes next, and it's a little bit more complex looking. It looks kind of like a little figure 8. That orbital also will hold 2 electrons, but those places in that figure 8 are the locations where the electron could possibly be located. And as you move up to D and F, these orbitals get even more complicated, and so the math to locate these electrons gets more and more complicated, but we're not going to be doing that. I just want you to see that these orbitals are really different from each other, and that's why we call them different sublevels. Okay, so our 4 sublevels, like I already said, are S, P, D, and F. And we're going to look up to the top left. You'll see that I have listed here the sublevels, and we're going to look at how many orbitals each sublevel contains, and then figure out how many total electrons fit into those orbitals. So every S sublevel can only have 1 orbital, but an orbital can hold 2 electrons. And that's true of any orbital in any sublevel. It can hold 2 electrons. So the total S sublevel with 1 orbital will hold a total of 2 electrons. I'm going to write that here. 2 total electrons fit into an S sublevel. Now as we move up to P, like it has that figure 8 sublevel, in a P sublevel there are 3 different orbitals, and that's why I've written 3 for the orbitals for P. And if every orbital can hold 2 electrons, 3 orbitals gives us a total of 6 electrons. As we move up to D, there are 5 D orbitals, so it looks like that little flower kind of shape you see. So there are 5 of those little flower shapes taking up space around the atom that are locations where the electrons could be. And if there are 5 of those, that means it can hold a total of 10 electrons. And then finally we move up to F, and there are 7 F orbitals. So F can hold a total of 14, because 7 times 2 electrons give us 14. All right. On the right, we have a diagram showing the energy of these different orbitals. So as you move through the energy levels, 1, 2, 3, 4, and 5, 6, and 7, the different sublevels have different energy. So just because S is such a simple type of orbital, it's generally a little bit lower energy than P. P has different properties because it's a little bit higher energy, and it's also a different shape. And as you move higher, you'll see that 4S is a little bit lower energy than 3D, and so there are some different things that we'll learn about the rules for filling up these orbitals as we get to that. Okay, so just like I said, the top circle type sphere, that is our S orbital. Below that we have our 3 different P orbitals. Below that are the 5 D orbitals, and below that are our 7 F orbitals. So there are really a lot of different types of shapes for orbitals, and electrons can be found anywhere within that shape. So that's just so you can see overall that there are a lot of different orbitals out there. All right, so we already said the number of electrons in each sublevel, but we're going to learn about how to write electron configuration. And let me write these numbers again. We had 2, 6, 10, and 14. Okay, so electron configuration is the arrangement of electrons into into energy sublevels. You can think of it kind of like the address of an electron in the highest energy level, or the address of a valence electron. So we're going to do an example. So we're going to use fluorine first. And fluorine has a total of 9 electrons. Okay, so when we start out writing electron configuration, we're going to start with, 9 total electrons. Just like it shows in the energy diagram, we always are going to start with 1s because it's the lowest energy. Okay, so we'll write 1s for the beginning of our electron configuration. And then, like we said before, 2 electrons can fit into an s orbital. So we'll put our first 2 electrons out of our 9 into the 1s. Okay, so then let's look back. After you go to 1s, the next thing to come is the 2s. So we're moving up to the second energy level. And how many electrons fit into an s sublevel? Just like in 1s, 2s can also hold just 2 electrons. So we'll put the next 2 here in the 2s sublevel. Alright, so now we've used up a total of 4 of our electrons, so that means we have 5 left. And the last 5, if we look back at the energy diagram, are going to go into our 2p energy level, energy sublevel. So 2p, and let's just make sure 5 are going to fit. In a p sublevel, we can hold up to 6 electrons. So definitely 5 electrons can fit into our 2p. So we're going to put 5 though, because that will use up the last electrons we have for fluorine. So the total electron configuration of fluorine is shown right here, 1s, 2s, 2p5. So this is the full electron configuration of fluorine. So now let's try this for magnesium. Magnesium, if you look at the periodic table, has a total of 12 electrons. Okay, so 12 total electrons. Okay, so every electron configuration is going to start the same way. We're going to start with our 1s, and that uses our first 2 electrons. Then we can go to our 2s, and that holds our next 2 electrons. Then 2p, and this time we're going to fill up our 2p because we have enough electrons to actually fill it. So 2p6 is what we're going to write here. So now we've used 2, 4, 10 electrons, so that means we have 2 left to use up all of our electrons. So let's look at the energy diagram and figure out what comes next. After 2p, the second energy level is filled up and we move up to 3s. So our last 2 electrons can fit into that 3s, and it fills up that 3s, and we don't have any more to add to the next sublevel, so we are done. This is the full electron configuration for magnesium. Alright. So we have a couple of rules that we're going to be learning about and how to fill up our orbitals and our sublevels. So the first one is called the Aufbau principle, and this basically says you start from the lowest energy level and you fill up as you move up in energy. So fill orbitals in order of increasing energy, which makes sense. Why would an electron want to go into a higher energy location than where it could go to a lower energy location? All right, so the next rule is going to be Hund's rule. Hund's rule will really make more sense after we move to orbital notation in a moment, but it says that we are going to put 1 electron into each orbital before we put its buddy electron or its pair into that orbital. Okay, so place 1 electron into each orbital in a sublevel. Before pairing. Okay. And the last one is the Pauli exclusion principle. The Pauli exclusion principle says that if an electron is in an orbital with a certain spin, it's the only electron that can be in that orbital with that spin. So when we're filling up the orbital notation, we'll explain what that means in more detail. But 2 electrons in the same orbital must have opposite spin. You can think about that being, the way I kind of think about that is like if you spin a top in one direction and then you spin a top in the other direction, those are 2 different spins. And so I don't really know further how to explain that, but these 2 electrons in the same orbital are going to have opposite spins from one another. Okay, so like we already wrote out, the electron configurations for these elements, I have them written here, 1s2, 2s2, 2p5 for fluorine. And we're going to look at how to take that electron configuration and turn it into something called orbital notation. And you're going to be doing this in class as well. So, like before, we saw that S, P, D, and F have certain numbers of orbitals and certain numbers of electrons that can fill up the whole sublevel. But we know that every orbital holds a total of 2 electrons. So we're going to use that to help us do the orbital notation. Okay, so fluorine. We have 1s orbital for fluorine, and in any s sublevel, there's only 1 orbital. So we're going to draw 1 line to be our orbital for 1s. The fluorine also has 2s, and because this is s, it only has 1 orbital, so I'm going to draw 1 line. Right now, these are empty orbitals. And then we have 2p. And whenever you have a p sublevel, you're going to have 3 different orbitals. So I'm going to draw those as 3 separate lines for 2p. Okay, so our 1s is completely filled up with 2 electrons. So I'm going to draw 1 electron. This little up arrow represents 1 electron, and it has an up spin. Just like the Pauli exclusion principle said they need to have opposite spin, my other electron in that same orbital is going to be a down spin. So that represents 2 different electrons in 1 orbital. So now that orbital is filled. And since there are 2 electrons in the 2s, we're also going to do the same for 2s. Now, once you have more orbitals, you're going to have to pay more attention to Hund's rule. Place 1 electron into each orbital in a sublevel before pairing it up. Okay, so we've got 5 electrons in our 2p. So we're going to put 1, 2, 3. So there I put 1 into each orbital before pairing. And then I'll put 4 and 5. So you'll notice that I have this 1 electron that does not have a buddy electron. And that is because this p sublevel only has 5 electrons in it. So we have that last available space for another electron. And if you recall, once fluorine becomes an ion, it gets that last electron, but we're not going to do that right now. This is just the neutral fluorine orbital notation, which we got from its electron configuration. Okay, so now let's try this for magnesium. Magnesium goes from 1s all the way up to 3s. So I'm going to have my 1s for magnesium, my 2s for magnesium, 2p, and my 3s for magnesium. Okay, so 1s is completely filled up, 2s is also filled up, then our 2p has 6 electrons in it, so that's filled up, 1, 2, 3, 4, 5, 6, and then finally I get up to my 3s, and it is also filled up with 2 electrons. This would be the orbital notation for magnesium. Alright, so in a few minutes, in the second part of this video, I'm going to explain to you how we can use the periodic table to help us write electron configuration, and then we will move to noble gas notation, and that should conclude our lesson on electron configuration.